this lecture for the Herschel Society in the Bath Royal Literary and Scientific Institution. The title is The James Webb, the Next Generation of Hubble Telescope, and the lecturer is Professor Martin Ward. I'm Tony Symes. I organise these lectures. Please note that this lecture is being recorded. For those in the room, if the fire alarm sounds, please proceed out of the way. Well, of course, I needn't repeat that because that only applies to those of you who are here. Please note that, again, rules of COVID restrictions, I've already said that. For the remote listeners, please check that you're on mute and move your video off all the time. You can turn them back on for the Q&A session at the end. If you have questions and you're listening remotely, please put the question in the chat channel. There are far too many of you for me to see raised hands, so you must use the chat channel for questions. We'll take questions at the end. The next lecture planned for the Herschel Society and the BRLSI will be on Friday the 1st of April. It will be delivered remotely from Texas and projected here at the Brilsey, and it's by Stephen Clifford with the title The Water Cycle of a Cold Early Mars and Its Potential Role in the Persistence of a Northern Ocean. Stephen Clifford is a senior research scientist with the Planetary Science Institute in Flagstaff, Arizona, where he conducts research on the hydrologic and climatic behavior of water on Mars. And some of you may have attended our lecture about water on Mars back in the autumn. The two lecturers have been in contact with each other so that one will lead on from the other, and there shouldn't be too much overlap. Back to tonight's lecture. Martin Ward was introduced to me by Bob Fosbury, who is on our committee, and he is an Emeritus Professor of the European Southern Observatory. He's the one who gave us the wonderful lecture on how the sun paints the sky, which is available as a highly recommended recording on the Herschel Society's website for anyone who missed it or wants to see it again. Let me hand over to Bob Fosbury to introduce Martin Ward.
Thank you, Tony. It gives me really very great pleasure to introduce Martin Ward. We're both astronomers. We first worked together in 1974 at the Royal Greenwich Observatory at Hurstmonceux Castle. Since then, we've wended our ways around the world in various places, occasionally crossing paths. But Martin has generated a high reputation from the breadth of his studies of astronomy. He's worked all the way from high energy astronomy, X-rays and below, through to infrared astronomy. Much of his astronomy has been to do with studies of active galaxies and so on. He's promised to introduce himself to tell you why he's talking about James Webb, so I won't stop him from doing that. I'd just like to say that he's ended up in Durham, as Tony said, Emeritus Professor in Durham, and he lives in a house which tries hard and almost succeeds in dominating the presence of Durham Cathedral on the hill next door. But yes, so Martin will tell you about the James Webb Space Telescope, very exciting project. Thank you.
Thank you, Bob. I'm just going to set the clock here. So it's great to see you all here, real people. I haven't seen real people in quite a long time, not in this number. Back in the old world, I saw many real people. I used to give lectures on cruise ships. But this is the largest audience since then. So I'm not quite sure how long this is going to last, this lecture, but I can tell you it'll only be between about 15 minutes and 2.5 hours, somewhere in that. Probably drifting towards the 15 minutes, but we'll see. So thank you for the introduction. I know some of you in the audience really well, and very well. In fact, I would say that if you have anything unpleasant to say about me, I do know where the bodies are buried, and usually that's meant metaphorically. But I'm very pleased to see you here, and I'll mention one or two of you as we go on. So, as has already been said, I'm Emeritus Professor at Durham University, and those of you that know about academia will know that Emeritus means forgotten but not gone. But I still do research. And also, though I'm from the deep north, Durham, in fact, I'm not from there originally because I pronounce it Bath, not Bath. So I'm actually from the south, from Essex. So as you know, I'm sure most of you know, everybody knows that it was launched, it says MIRI here, it should be the JWST, was launched 25th of December 2021. And just a word about Durham and about 2 minutes about me. I hope that's not too long. Oh, I meant to say I wanted to welcome the people online. Let me just backtrack slightly. So welcome everybody online. Sorry you can't be here, but I'm sure you're there in your pajamas with your gin and tonics and other things that you do at home. So welcome everybody online. So just a few minutes about me, not more than that. Durham hopes to be the city of culture in 2025. It has a very long history of science, although it wasn't called science in those days, going back to the Venerable Bede. Those of you that know anything about history will know that he was very interested in natural phenomena, and amongst many other things, he actually introduced the lunar calendar, which is the reason why we can never figure out where Easter is. I think it's late this year, but we have him to blame for that. This is the view, not quite from my house, but nearly from my house, and do come and visit Durham. It's a charming city. It has a castle, has a cathedral, and rather extravagantly, it has two saints. It has the Venerable Bede and St. Cuthbert, not just one as other places have. So as I said, a few minutes about me. So this is the history of me, very briefly. The Royal Greenwich Observatory here on the right, Herstmonceux Castle, the Fosbury Turret. Is it left or right? No. Left, Fosbury Turret. That's where Bob was, and I forget, I shared an office because I was only a student in those days. Those of you that might wonder, what the hell's a castle got to do with astronomy? Well, it was actually the home of the Royal Greenwich Observatory, not the Royal Observatory Greenwich, which is the Maritime Museum in London, for many years. And in fact, it had the largest telescope in Western Europe, the Isaac Newton 98-inch telescope, for many years. But it did suffer from a problem that its altitude, you know, many of these astronomical sites are at 10,000 feet, 15,000 feet, maybe even something like that. And the Isaac Newton, I think, was an altitude of 30 feet. And that's because that was the height of the building. So it wasn't a great place to do astronomy, but I enjoyed my time there and it was good fun. I think Bob enjoyed his time there as well. Briefly then, on the left-hand side is me, because I haven't changed very much. I was a less substantial person in many ways in those days. This is me on the catwalk of the Anglo-Australian Telescope where I did my PhD. I should say that I'm not a rocket scientist. I borrowed this from somebody who was more of a rocket scientist than I am. I'm what I would call an end user, so I have tremendous respect for those people that build things, widgets. In fact, I have a couple here which I'll explain later, and you can come up with those, rather a lot of you, perhaps I'll hand them round. They're not very fragile. They're bits of the James Webb Telescope that are up there, but not the actual bits. They're exact copies, so they won't miss them. You can have a look at them. But I'll come to that a bit later and I'll pass them round. I think it's fun to actually see for real, and they're full size. They're replicas of what's up there. So my association with the James Webb goes back, I don't know how many years. Before it was called the James Webb, it was called the Next Generation Space Telescope, echoes of Star Trek, I suppose. And then it became changed to the name, which I would explain why it's called the James Webb a bit later on. And my association began rather sort of administratively as chairman of one of ESA's committees, the European Space Agency committees, but that wouldn't qualify me much to be involved. But I then became a member of the science team, along with many other people, of one of the instruments aboard the James Webb, which I'll explain later on. So that's my credentials, I suppose, for knowing something about it. Although I am acutely aware that there are at least a couple of people in the audience who probably know more about the technical side than I do. So you can ask them difficult questions afterwards. I'll pass it over. So I'm just one of probably by now 2,000, because the number increases, scientists involved in the James Webb. This is a full-size replica. It's not the real thing that was before launch, because they wouldn't leave it out in the parking lot. It's an exact replica which was used for public relations purposes, but it gives you an idea of the size of the telescope. So I'm very keen on outreach activities. As I say, here's one I made earlier. I had an exact replica of one of the 18 hexagonal mirrors made by a bathroom company in the north of England, and I had them coat it in bronze, because bronze looks more like gold than gold does, and that's the actual coating that's used for the James Webb, because it reflects infrared light. It's not that it was so expensive they thought we'll make it out of gold. It's simply that is much more reflective for infrared, whereas normal, well, say normal, optical ultraviolet waves are reflected by normal silvered or other surfaces that look like a normal mirror. So that's why it is, and it's useful, this, for public relations exercises, taking to schools and so on. And nearly finished with the history, just a short couple of things more. Durham Observatory is the third oldest in England. You can see here on the left-hand side, this is what it looked like when it was first built, and on the other side, what it looks like now. The reason I mentioned this is just because it links in with my interest in outreach. And I want to turn this into a centre for outreach of astronomy, which I hope in the fullness of time will be available for school children and people to come and use small telescopes. Much as, if there are amateur astronomers here in the audience, you may have heard of the Kilda Observatory, the dark skies in the Kilda forest. So this would be, if you like, the town version of Kilda, and they've offered to help us with open nights. So I'm looking forward to that very much. And the final thing then on this is, it's very small writing, but you can see at the top here, Carrington was actually one of the assistant astronomers at this observatory, and those of you that know a little bit about the history of solar physics will know something called the Carrington Event, an enormous solar storm, which, if it happened now, would be really bad news for communications around the world. And so there is a nice connection there with the sun, and I like that because it means we can have people come and visit the observatory during the day, and we can talk about sunspots, project the sun and the rest of it. So it's not just an evening event. And the final thing about Durham, and this is aimed at a particular person in the audience here, you know who you are, it's Maurice Tucker. This is the great hall of the castle at Durham. Maurice was the master of the castle, and I've had many happy meals there. This is me standing underneath Temple Chevallier. By the way, it's not Chevallier, no relation to the French Charpentier. Anyway, that was him. I don't look much like him. I'm working on the beard. He's the guy above me with the long beard. So that's it for the history. I hope that wasn't too long. So why do we do astronomy at all? Well, that could be and is a big question and topic of many lectures, but not this one. But I just want to say one of the reasons that we do astronomy, at least I think, is because we want to know where we are in the universe, what is our reason in the universe. Well, we can't really answer that, but studying the universe puts things into context. Universe is big, really big, as they say, and we can see perhaps what our position is, and the fact we can understand even a part of what the universe is rather remarkable. The other reason we do astronomy, this is just one aspect, of course, is the question of, are we alone in the universe? And this had a huge boost several decades ago now with the discovery of the first exoplanet, one beyond our own solar system. Now, this is very, very big business. We know about 4,000 exoplanets, many of them in multiple systems, so not just one planet per star, maybe 4 or 5 planets. But of those 4,000, whatever number it is now, increasing practically every day, only a small fraction of them would be suitable for life as we know it. That reminds me again of Star Trek. So there might well be life forms that we don't know of, and they could exist. But we often think more in terms of where could there be a twin of the Earth, somewhere that would possibly support life as we know it. And this is just an artist's impression of a twin Earth, which is near the centre of a galaxy. Of course, it's projected centre of the galaxy from somewhere else. So back now to to the things in hand, things look very different depending on what wavelength, or if you like, energy we observe at. Now, I was never an amateur astronomer. I'm sure many of you were. I got into science, perhaps through science fiction. I did have my own little telescope, but it was all too cold, and going out in the garden, and then it was cloudy, and you've seen one star, you've seen them all. So after seeing the moon and seeing the planets, I kind of got bored with it. But what's very interesting is things look very different. The Orion constellation here, seen in X-rays. We have an expert, a very famous expert in the audience, Belinda Wilkes, who was in charge of one of the principal X-ray satellites called Chandra. And you can see here in X-rays, things look entirely different for reasons I can't go into. It's a whole lecture of its own, basically because we're not looking at the same emission processes as we are in the optical. And I did tongue-in-cheek once on a cruise ship say, I'm thinking of going to the business of X-ray astrology, where we have all the constellations of X-ray emitting objects, and we make our own constellations, and we cast horoscopes. And of course, it's much more genuine because it's much more energetic, so it must be more realistic. And then somebody came up to me afterwards and said, could you cast my horoscope? I didn't think they quite got the irony of it. But there may be money to be made in that area. So just to go right across the spectrum now, I'm going to focus on the James Webb, of course, which is the infrared. But the Whirlpool galaxy, otherwise known as Messier 51, looks very different from the radio here in the left to the infrared, which is closer to what we're seeing with the Webb. In fact, these wavelengths that this picture was taken in rather shorter than the Webb, but the principle is the infrared. The optical, the ultraviolet, and the X-rays. And again, I can't go into too much detail, but you're seeing either different types of stars or different processes entirely, as in the case of X-rays, which come from accreting objects onto neutron stars and black holes and exotic objects. So things look very different. And to get the full picture of what's happening in an object, it's very good to assemble these things together. So if you like, it's a holistic approach to astronomy. But depending on what you want to do, you can answer some questions specifically by looking in one band, but it's sometimes better to look right across the bands. Just a brief word about, I've said here, the European Space Agency fleet across the spectrum. It's a little bit out of date now, but there are many, many satellites up there, and this is the astronomical fleet. There are other things that look at the Earth, Earth observation satellites and so on. So this is just one snapshot. And of course, there's another version of this for NASA, and indeed other countries such as China, Japan, other countries have their own missions, but not quite at the same level as ESA, which is a collaboration of many countries have. And I will just give a plug, which I'm very happy to do, for one mission called Gaia. And we have in the audience here somebody, I will name, if he doesn't mind, Michael Perriman, who is absolutely pivotal in a whole area of astronomy called astrometric astronomy, measuring the positions of stars. That might sound a bit mundane, but it absolutely isn't. If you want to learn about the Milky Way, its origin, its history, and everything. And Michael, I think we owe you a great debt for working on this, and also the previous mission called Hipparchus. So I hope you aren't too embarrassed. Well, you shouldn't be. Okay, so now looking at the wavelength that I was talking about across the wavelengths. So in this case, then, we have right the way from the shortest wavelengths, the highest energy, up to the radio shown here. And the visible light is only a very small fraction of the total electromagnetic spectrum shown here. And so the visible light and a bit of the ultraviolet light is what the Hubble studied. And here we go, the next, there we go. That's the infrared window. So you can see, even put together, it's still not a huge amount of the whole spectrum, but it's a very important amount because there's a lot of information contained within these windows, as I'll explain a bit later on, in terms of imaging and also in terms of spectroscopy. So just a word about the heritage of space telescopes, and this does go back a long way. Like most astronomers, scientists, we live on acronyms. So the IUE stands for the International Ultraviolet Explorer satellite. And back in the good old days, you can see this lady here sitting here would not have been allowed to sit here without wearing a white sort of COVID type suit with a helmet on and everything. But in those days, they didn't worry too much about people sneezing on the instruments. So you can see here what it was like. But the thing to note here is that it's really small. Its aperture, I think I got this right, was 18 inches. Somebody can correct me if not, but I think it was only 18 inches. So imagine this as almost the size of an amateur astronomy telescope in your back garden. But it did enormously more things than your back garden 18-inch telescope would do, because it was looking in a waveband that couldn't be observed from the ground. It was supposed to last about 4 years. That was the kind of lifetime that was assumed. But in fact, it lasted from 1978 to 1996. And it was an amazing instrument. It didn't take images. It only did spectra. I say only. But that was sort of one of the big drivers for doing the Hubble Telescope, which was much bigger and did imaging and did spectroscopy. And I worked using this telescope in my youth, as did Michael Perriman, and I'm not sure whether Bob ever used it. Yes, Bob used it as well. And it still is useful for even today. We're very interested in the variability of some objects, in particular some stars that vary a lot because of the accretion, or they evolve and change, and quasars, these very energetic centers of galaxies that have a black hole at the center and material falls on. Sometimes they change their energy output by an enormous amount. And why is that relevant? Well, if we take a spectrum now, it's very interesting to compare it with the spectrum of long, long ago, and to see if we can understand the massive changes in terms of what's happened in the spectra. So the IUE database, as we call it, is still enormously useful, even though we have much more powerful telescopes now, the Hubble, for example, as well. So now I'm going to talk a bit about the Hubble Telescope as a precursor before we get to the James Webb. So who was Edwin Hubble? Well, as you can see, he was a gentleman astronomer, as you can tell from the tweed jacket and the pipe, and he did many things, but the thing he's most famous for is studying distances of galaxies. And again, this is another topic of the whole lecture, but before Hubble, it was thought perhaps that these fuzzy blobs in the sky, well, some of them were nearby clusters of stars like the Orion Nebula, but some of them weren't. Some of them were in fact island universes. We don't use that term anymore, but they are galaxies like the Milky Way, but you can't resolve, in other words, see individual stars. So they're just sort of fuzzy bits, hence nebulae. And he was the person that managed to determine their distance by the fact that some stars change their magnitude, that's brightness, in a very regular way. And the period between up bright and down faint, that time between those is related to their brightness. So they become what we refer to as a standard candle. It's a rather old-fashioned term, but simply what it means is, bring it a bit more up to date. If you have a 100-watt light bulb and you have something that measures energy and you take it into a dark field, you can actually work out the distance of this 100-watt light bulb, if you know it's 100 watts, by how much light has got to your detector. It's called the inverse square law, which is pretty much what Hubble did. And he then produced this famous paper about the fact that some galaxies, the further away they were, the more they were speeding up, coming away from us. The distance was related to their recession velocity, which is the expanding universe. Now, there's a little wrinkle in this, in that he got the Hubble, called the Hubble constant now, completely wrong, because there was a mistake in the particular type of variable star that he used. But that doesn't matter. The principle was right, and then they refined it later. And I wonder in several hundred years' time whether the paper published in 1929 will become more famous than the Wall Street crash, but we won't be around to see whether that actually happens. But in terms of understanding the universe, it certainly was more important than the Wall Street crash. Hubble Telescope was launched April the 4th, 1990. I'm not sure what I was doing. I don't think I remember it that well, although I was involved to some extent later on in it. But that's a very long time ago. In fact, you do the maths. So it was the 30th birthday, not long ago, and we were planning to have a big birthday party in London at the Royal Society for it. But unfortunately, COVID intervened, and so it had to be done virtually. So it wasn't quite as nice as it would have been otherwise. You can see here an impression of how the Hubble was launched. It was launched from the bay of the Space Shuttle. It's not entirely filling the bay, but it's quite a big chunk of the bay, which to some extent limited the size of the mirror, the diameter of the mirror. For example, they couldn't have had one, I didn't say what it was, 2.5 meters across. It's much, roughly. They couldn't have one twice the size because it wouldn't fit. Now, there's a clever way around that, which I'll come to in a minute with the James Webb, if you can't fit the mirror in to the launch vehicle, be it the shuttle or be it an Ariane rocket. There is a way that one can get around this. But the Hubble, in fact, was a single mirror, and you can see here being deployed. So that was all great, except, if you remember, I certainly do, what went wrong with the Hubble? So it got launched, no problems. It got into the right orbit, no problems. Switched it on, no problems. The camera was turned on a particular object, and instead of seeing a nice sharp image, it saw what's on the right-hand side, horrifically blurred. Now, initially, I think for a few seconds perhaps, they thought, oh, that's all right, we'll twiddle some knobs, because they had, like when you have a telescope or binoculars, you have the adjustment for the focus. They thought, all right, we'll just adjust the focus, until they realized it was massively out of range for the focusing. So they planned on it not being perfect, because it never would be, but the amount of twiddling of the knobs that were possible to make it in focus was nowhere near enough. So what could have gone wrong? Well, now I have to give credit to Bob Fosbury here, who produced this very nice picture, and he could explain this better than I, but I'll give the simple version. To measure the focal length of the mirror, that's the really important thing, is if you're going to put a detector to do great imaging, it's got to be absolutely at the focal length of the telescope for a pristine focused image. So you want to know the focal length accurately, very accurately. And so back in the good old days of my O-level physics, those of you that did that sort of thing, there was a thing called no parallax, where you have a pin and you've got your mirror lined up on the bench and you fiddle with this pin, and then you see an image of the pin. And when the image of the pin upside down, is upside down, I think, goes with the actual pin, you measure it, and that's the focal length, or is it the centre of curvature? One or the other. Factors of two, you get it right. It's if you're doing O-level physics, it's easy. So you could do that, but of course that's no good. I mean, how would they possibly rely on no parallax to get the focal length? So instead they used lasers. Much better to use a laser. And that would have been great. Interferometry is the technique, which I said, you don't need to know the details. But what they wanted to do was to measure the distance, as you can see here on the left of the two panels here, of the lens should have hit this rod, and then they would measure the focal length to fractions of a micron. They would measure that, and then they'd say, right, we'll adjust our little knob for the focus such that if it's not quite right, we'll fix it. But instead of measuring it to a fraction of a micron, unfortunately the light hit the top of the cap where a bit of paint had chipped off. And so they measured the distance which they thought was the focal length, and the difference was 1.3 millimeters, which I think you'll appreciate is rather more than a micron. And so it was hideously wrong, and they didn't know that at the time. And as I say to my students when I talk about errors, this is the difference between precision and accuracy, because the measurement was incredibly precise but totally inaccurate. And there is a difference there, and there's a moral to it. And the odd thing is, if they'd have done another way of measuring it, which was perhaps a bit cruder, but just a kind of, we call it a sanity check, have we got this right? Has something gone horribly wrong? They would have known straight away that they'd got it wrong. But why would you do that when you think you've measured it to a micron? You didn't bother, and they didn't bother. So what happened after a number of, I forget how long it was roughly a year, Bob, do you remember how long it was?
3 years.
3 years later, yeah. They sent up a sort of rescue mission called CoStar, and what that was more or less was contact lenses. So rather than replace the whole mirror, which would have been a massive exercise, what they did instead was they put little mirrors, so not quite contact lenses, principle the same, in the instruments of the Hubble, the camera and other things, to exactly correct for what went wrong. I wear contact lenses and I can see almost as well as people that have good eyesight with them, except they use mirrors. And my friend here on the left-hand side, called Jeff Hoffman, was one of the people that went up there and fixed it. So one of the heroes. And of course, NASA got huge credit for this. I mean, Buck Rogers saves the universe. They went up and they fixed it, but people sort of may have said, well, why did you screw up in the first place? But anyway, they managed to fix it, and that was great. And here's me on the right-hand side with my friend Jeff Hoffman. I think I had a big hair day that time. That was in Oxford at the time. And anyway, he's a good friend of mine, and that was great. And then it was fixed. And just as an aside here, I'm very impressed with the Hubble, although I haven't used it as much as some people. So I commissioned some stained glass panels for my house, which has been alluded to in Durham opposite the cathedral. And these are the stained glass panels, which I won't go through, but there's a supernova here. Some people may recognize it. There's the Hubble Deep Field, and these blobs are supposed to be galaxies, and then there's interacting galaxy. You know, I'm very proud of it. It's in my library. If you come to Durham, pop in, I'll show it to you. So that's all very well, isn't it? But I'd come to a fundamental question now, and that is, why are we going to put things in space? What is the point, given that the Hubble mirror was 2.5 meters across, whereas the VLT, I'm sure many of you know what this stands for, the Very Large Telescope, is 8 meters across, and there's 4 of these in Chile, so you could combine them and make it a bit bigger, but that's difficult. There's the GMT, the Magellan Telescope, which hasn't yet finished, 24 meters, but it's made up of a number of individual mirrors, a bit like the James Webb, which I'll come to very shortly. It's a number of mirrors which are brought together to give more collecting power. And there's the ELT. We're very unimaginative, as you know, in astronomy. So this is the extremely large telescope. And there was even a possibility, but I think it's now gone the way of no money, called the OLT, the Overwhelmingly Large Telescope. So you can build these things. ELT will be happening. It's not just a figment. And here it is. So these aren't real mirrors, these are mock-ups. So this is the size of the mirror, made up of many, many 400 hexagonal segments, each one roughly the size of the James Webb single 18 elements, roughly speaking. I mean, you can see people there, it's pretty damn big. So why would we bother going into space? Well, here's the maths, but it won't be too much maths. It's the only equation I'm showing, I think. A thing called resolution, and that is how accurately can you define detail. And it's simply speaking, it's defined as if you had 2 stars, for example, it applies to any image, but if you had 2 stars and they were brought closer and closer together, at what point would they seem like they were 1 star? And the answer is the resolution, radians is a sort of another version of saying degrees. You can convert into degrees if you want. There's a very simple formula which relates the wavelength, whatever you happen to be, over the diameter. So in this particular case, the bigger the mirror, the better it is, because you want theta here on the other side to be very tiny, because that tells you how fine a detail you can see. So you want D really big, and you want lambda really small, but then lambda is whatever lambda is. You don't necessarily have a control over that. If the Hubble is being used, then it's optical or ultraviolet. If the James Webb's being used, then it's the infrared. So this is the formula, and that's what we want. So, okay, done that. But the problem is, on the ground, we have a problem, and that's the Earth's atmosphere. It's quite useful, actually, because otherwise it'd all be dead if it wasn't here. But it is a problem for astronomy, because it makes things wobble. And if you've ever been out at night and you've seen stars twinkling, well, they don't twinkle. It's quite nice, it's quite poetic to see them twinkling. but they don't. This is because of the atmosphere. There are little lumps, if you like, of gas, the atmospheric gas, at slightly different temperatures, moving about, and that causes it a bit like a mirage, sort of like a mirage. So it makes things wobble. And if you didn't have that, if you had a clear view, obviously this is the moon, I could have shown you a star, but I thought it was fun to show you the moon. You get a lot clearer view of the thing if you didn't have the atmosphere. So that's why we do it. However, it is possible to correct for the atmosphere using what we call laser guide stars. This is a spin-off from Star Wars, because if you're of a certain age like me, or maybe even a bit younger, you might remember the Ronald Reagan period when they were talking about having these battle lasers on top of mountains that would use lasers to shoot down incoming Soviet Union, as it then was, multi-warhead missiles that you needed to correct the atmosphere wobbling in order to hit these missiles. Of course, there was a flaw in that argument, and that is you can only die once. And even if you stop 90% of the missiles, 10% get through, so what's the point in the first place? And also, as Martin Rees, the Astronomer Royal, which he was at the time, put it, in this case, in the case of science, he said, we proceed by trial and error. In the case of Star Wars, there's no trial, only error. So let's get on to the James Webb. That is what this talks about. It goes roughly 10 times longer wavelength than the HST, the Hubble Space Telescope. And one of the reasons, there are several reasons, and I'll come to the two principal reasons, why that is a good thing. One is if you have a lot of dust, and there's a lot of dust in the universe, maybe not in the very, very early universe, but certainly as the universe evolves, stars explode, supernovae, dust is formed. In fact, a lot of the solar system, what we call the debris disk, is formed of material, some of it's dust. So a lot of dust around. And the Eagle Nebula, sometimes referred to as the pillars of creation, is shown here on the left-hand side in the optical, and on the right-hand side in the, sorry, I think that may be the wrong thing there. That's, visible IR, yes, it is correct. So in the IR, you can see through the dust, and you can see the stars behind it. So it's a way of penetrating obscured regions of the universe. And there are periods in the universe and objects in the universe that are heavily obscured. So if you wanted to see what processes are happening within these obscured objects because of dust, you need to go in the infrared. And here we have a link with William Herschel. So I'd say discovered infrared astronomy, but he did discover something which was in fact serendipitous because he wasn't looking for the effect. He discovered it when he was trying to do something else. It's very simple. You must have seen in the textbooks the famous Newton experiment with the prism, where you get the light, and it's very easy to do. You can do that with any small bit of glass and other things like a CD. If ever you have a CD, people don't use them anymore. You can get a prism and you can get an optical spectrum. And he had 3 thermometers, and he put them not randomly, spread them across the spectrum to see if the temperature would go up. And indeed, the temperature did go up, but oddly enough, whether he mistakenly put one beyond the optical spectrum that we can see or not, whether it was by design, there was one that was beyond the spectrum that we see with our eyes. It was at longer wavelength, in other words, beyond the red. And the temperature on that thermometer went up, I believe, more than the other ones. And took a long time before people explained this, but this was the first indication that the sun was producing radiation at wavelengths we could not see, beyond the visible. So people in the society here should be very grateful, I certainly am, to William Herschel for this discovery. As an aside, many of you will know this, I think he's the only famous astronomer who's had a very large ground-based telescope and a satellite named after him. Did anyone contradict that? So the William Herschel telescope in La Palma is a 4.2 meter diameter mirror. And then there was the Herschel far infrared. I think he's the only person who's had two major things named after him. So is that right, Bob? Could be. So we use that because we use the infrared because it penetrates through dust. And perhaps I should have shown this slide before, but the reason fog lamps are orange or yellow is because they penetrate murk more than normal sort of whitish, bluish light. So there's a practical reason why we do it as well. And this is just a bit of fun, really. So the infrared is also a good way of detecting the temperature of a body. And here we have cute little animals like the adverts, that I forget what they are now, the meerkats, possibly, and a crocodile, or is it the alligator? Who knows the difference? I don't. It doesn't matter. One's warm-blooded and one's cold-blooded. So this is an optical picture of them both. And if you look in the infrared, you can see that the cute little meerkats are booming away in the infrared, whereas the crocodile/alligator isn't. So it's a way of temperature, which again is why police, the army, and people that are searching for people in rubble use the infrared, because sensitive to our body temperature. I said it was the only formula before, but here's another one. It just shows that the cooler the object, shown here in the temperature 15,000, 10,000, 5,000, the more the peak of the emission, the energy emitted over the whole of the emitting object, is moved towards the red. So if you want to study an object which is very cool, for example, you're better to look at it in the infrared, because you'll have more sensitivity in the infrared. And the atmosphere is a real problem when you go to the infrared, because the atmosphere is quite hot by the standards of these temperatures that we're looking at. Not the 5,000, of course, absolutely not, but that's what we call a black body. That's a heated object. But anyway, the atmosphere is quite warm, and that would therefore make it very, very difficult, if not impossible, to look at objects of roughly the temperature of the atmosphere. So we're blind when you get beyond a certain wavelength in the atmosphere. Now back to the James Webb. By the way, I'm never quite sure what I should call this. I think we're supposed to call it the Webb Telescope now. I have a problem because I've been around the James Webb so long, I tend to call it JWST, and it does have advantages. And that is when you type it in Google, if you put Webb in Google, guess what you get? 5 million hits. And if you put JWST in Google, you don't get so many hits. But probably supposed to call it the Webb Telescope. Why was it called that? Well, there's lots of stories here, and I'm happily be contradicted. But it is said that the people high up in NASA, whoever they might be at the time, were fed up with all these satellites and famous telescopes being named after Einstein, Herschel, Maxwell, all these famous scientists. So they said to each other, let's have one named after us administrator people. So indeed, he was not the administrator at the time it was named. He was the second chief administrator of NASA during the Apollo program, which of course many people would say was a highlight. Landing on the moon, yes, I think it probably was, if you're interested in that sort of thing. And so they thought James Webb is a reasonable thing to do. Now, I'm not going to go into this because it's beyond what I'm confident to do, but there was a bit of a backlash shortly before launch about keeping it named after him, because there were things in his background that were unfortunate, and it was looked into, and in the end, NASA came up with the decision that they would keep it as the James Webb. But there was controversy, but we are now calling it the Webb still. So here's a picture of the two telescopes to scale. So you can see then the difference in size and, to some extent, in complexity of the Webb compared with the Hubble. And the big difference being that the mirror, the big thing is that the mirror is much larger. So I need to speed up, but that's okay. Some of these slides only take a few seconds. So this is the picture of the Webb and the Hubble. And there we go, 2.5 meters versus 6.5 meters across with these 18 segments. And the area then is 6.8, let's call it 7, shall we, times, because that's the collecting area you're interested in. The diameter is all very well, and it is related by a well-known formula to the area. But you actually want to know how many photons are going to be collected. So there are a number of instruments on the Webb. One is called MIRI, the Mid-Infrared Instrument. One is NIRSPEC, the keys in the acronym, Near Infrared Spectrometer, and one is NIRCam, Near Infrared Camera, and one is the Fine Guidance Sensor. So my involvement on the science team is in MIRI. As I say, it's horses for courses. depends what you want to do. If the thing is not heavily reddened, obscured by dust, then maybe you go to near spec, because why make life difficult? The sensitivity is less in the far infrared. By the way, the fine guidance sensor is used for lining things up. So it's not really a science instrument, but it's essential to the Webb. This just shows you the wavelength coverage of these instruments. And so you can tell from the name that the mid-infrared instrument goes to the longest wavelength, which is up to 28 microns, and the near-infrared, by the name, goes down to the shortest wavelength, which is about 0.7 roughly. And the near-infrared spectrometer is from about 1 to about 5. So these are complementary in many ways. So the Webb's journey to L2, some of you have followed this, was complicated, but everything went perfectly to plan. I'm afraid the writing's probably too small to see here, but it is now 1 million miles from Earth. And I think this is where, can we show this, Bob? I wanted to show this movie. It only lasts for about a minute, but I think that's the movie we just started.
Yeah. It's showing here, yeah.
Is that great? Oh, that's wonderful. So by accident, not by design, we're watching it. It lasts about a minute, and then we have to go back to we don't go back yet. So what I wanted to show you here was the complexity. Of course, this is a simulation. We didn't have a camera to show you this, but you can see the solar panels, the sun shield, which is required to keep it cool, this massive sort of triangular thing, coffin-shaped thing shown here. And you can see then the mirrors coming up. Of course, they had to be folded because they needed to fit into the top of an Ariane rocket. And I thought that they called the top the shroud, but I think that's rather an unfortunate term. And so they call it something else now. I think the top of the rocket where it fitted. You can see now the deployment. It's really finished. You can see the sun shields coming out. There are hundreds of moving parts here, actuators. You can see there are 5 different layers. Why are there 5? That's because the first layer absorbs some heat, but it back radiates some of that heat. And then the second layer absorbs the back radiated. There's less and less and less and less. And by the time it gets to shielding the mirrors, it's tiny. So you can see now the mirrors are deployed. It's nearly finished. Go to the end. Underneath here, you can see something which is designed to counteract the effects of angular momentum. Bob will explain this, but it's an essential thing, otherwise the telescope would have difficulty in pointing. And we're finished. And so at the end of this, I always say, when I've shown this, what could possibly go wrong? Unfortunately, nothing did go wrong, unlike maybe this presentation. So we'll see if we can get back to the last few slides. So this is the selfie I've already said, and then we've done this already, lining up the mirrors, and we're nearly finished. So the diffraction pattern, then, this is what happens when you get a very sharp image. Now, many children, not all of them, will think that stars actually look like this with a little cross like this, but it doesn't look like this. It's only because of the structure that the support mirror, the secondary mirror, is used. It's got to be held in place, and that causes these spikes shown here on the left. If picture was taken through a refracting telescope, one with a lens, you wouldn't see these spikes, but you might see rings because that's the signature of there being a circular lens. So in the case of the James Webb, it's very complicated because each of the hexagonal mirrors, it has a sort of 6-fold, because of the shape, sort of symmetry. And so you get this very complicated pattern, but it's quite beautiful, and nevertheless, we can correct for this to some extent, and this is what we will get. So we've now got, so far, the image shown here on the right, but we will get 5 times better when everything is lined up. But this is the pattern you get from one of the 18 mirrors, and when you line everything up, you will get a better image by the ratio of the size of one, which is 1.4 meters, to the size of the whole thing, which is 6.5 meters. So you get a 5 times improvement, which will be great. So finishing off very soon. So this is what it looks like at the back here. It has to be done super accurately, as I said before. What will the James Webb see? Quick on this. It will see the beginning of things in the universe, the so-called dark ages, which are very difficult to see with the Hubble, partly because of the red shift. So although light might have started off as blue, by the time it gets to us, it's red. And so objects which were initially blue when they were formed, by the time the light reaches us are red, we will be able to see these very first galaxies forming. And we will see also nearer objects that are, in cases of formation, interacting galaxies, dusty galaxies, and so on. We will not see a black hole. It's not possible because you can only see the shadow. This was an image done some years ago now using a whole range of telescopes. The James Webb won't show us that, but it will show us inside the galaxy near to the black hole, and it will show us things that are happening near to the black hole. This is an active galaxy. In other words, it has a black hole at the center, which is accreting material and throwing out gas. So there's an oddity here. You think of gas falling in, but actually stuff is going out as well. And we will study both things falling in and things being thrown out. And these are a couple of examples of galaxies which are very dusty and nearby, which we will be able to unveil, if you like, what the black hole is doing by looking with the Webb. A spectrum is worth 1,000 images. Here's a spectrum. That's because a spectrum is 1,000 images in a sense. We see emission lines and absorption lines which tell us a lot about the physics of the object, more than it's complementary to imaging, but it can tell us about the astrophysics. Exoplanet atmospheres, we will not see images like this. Obviously, this is supposed to be an exoplanet, but we might see, these are NASA publicity shots of visit these exoplanets. Double star where your shadow always has company, and another exoplanet where there's no star, so the nightlife never ends. These are just publicity shots. You can get them off the web if you want to put them on your wall. So, what it will be able to do is look at the spectrum of exoplanets and maybe look for interesting features in the atmosphere. Having to go rather fast now, but we are on the last slide practically, and that is, we're now almost there. There will be many other things, and I just class them generically as iconic pictures, as indeed, I think you'll all agree, I had this on my wall as a student, referred to as magnificent desolation of the Earthrise over the moon, which has such an impact in terms of how one feels about the Earth, the pale blue dot, as Carl Sagan put it. So this is an iconic picture. I'm not saying the James Webb will have this sort of picture, but it'll have other pictures, which I think will become iconic as well. And there will be the unexpected. And I haven't faked this up. This is actually an image taken by a ground-based telescope. No kidding. It's not a fake news. But of course, when you think about the chances of random orientations of things, it's going to happen. And this is an example of what did happen. So there will be the unexpected. And it could be the unexpected turns out to be at least as interesting as what we thought we were going to see at the time. So all I would say now is we are at the beginning of the James Webb. This is only the end of the beginning, as I sometimes put it. It's at L2, it's cooling down because you can't use the infrared cameras until they're cool enough, which will be for another few months. And then we will get the first images, which will be very beautiful, and I look forward to seeing them. So all I can say now to finish off is thank you and watch this space. I just want to say one other thing, and after the event, if you want to come up here, I know there's a lot of you, but here's a bit of the NearCam, I think it was, or NearSpec, made in Durham. So this is exactly what's being flown out there 1 million miles from Earth. It's just a mirror, just a relay mirror, and this is part of a spectrograph here called an image slicer. So you can come and look at these, take a picture, pick them up if you like. I'll leave them here for you to look at afterwards. Any questions?
Thank you very much. We don't have any questions in the chat channel at the moment. Let's start off by taking a question from the back there.
Martin, thank you for that was I think tremendously informative and beautifully talk and very kindly made reference to my own.
Totally justified.
But one thing you again made reference in passing. Martin shared, I want to avoid this becoming mutual but in addition to his other academic responsibilities and achievements, Martin shared his strongly working group with his in, I think, 2000 and 2001,
Yep,
something like
close.
that.
A space
And
odyssey.
it was a very, so this is a very important advisory committee.
Michael, can I ask you to come and speak to
Well, I should come.
because the remote audience won't be able to hear you.
Don't go through it all again.
I won't go through it all again. But what am I speaking to? No. Oh dear, how embarrassing.
Just say I was chairing or something.
Well, you were chair of the Astronomy Working Group in 2000-2001, which was a very important period for the European Space Agency because it was when a number of the future science programs were actually decided upon and pushed through as part of the Horizon 2000 Plus program. So it was a very, very key moment. And in fact, you didn't mention this, but you were influential in getting the European contribution to the James Webb Telescope actually through the whole advisory process. And I was asked to pass on some acknowledgements and thanks from the James Webb Space Telescope project scientist at the time, Peter Jacobson, who looks back and says how influential this was in getting this program actually on track. And you did exactly the same for Gaia. It was a very critical period for Gaia. And it was your committee and your very, very strong recommendations which actually got this through. You've talked about the technology. I think we're looking forward to a fantastic period in science. Again, you could talk about many things, but one is the stunning scale of human collaboration involved in these projects. And I think there were so many steps along the way, and you played a great part in that as well.
It's a long haul, but thank you very much.
Thank you very much. It was fascinating. It's an area that I'm passionate about anyway. My two questions relating to this.
Can we have just one question for the moment?
They're related.
Make it a quick question because I'll need it to be repeated for the remote audience.
Okay, I'll repeat it.
First question, the two are related anyway, is to do with the infrared, the nature of infrared photography. Because the example that you showed us of the warm-blooded and the cold-blooded creatures, you said that the advantage of using infrared technology is that it will give you a better picture of the cooler objects. But when you looked at the example, the cold-blooded creature was not really as clearly seen as the warm-blooded creature. So that was the question I wanted to ask.
Very good. Okay, well, the quick one for that is that it depends on the actual temperature. Of course, the cool-blooded object, animal, whatever it was, reptile, probably had a temperature similar to its surroundings, whereas the warm-blooded object, so it's a contrast, a matter of a contrast, and the mercats were much hotter than the surroundings. So if you have an infrared picture of your face, some of you may have seen this, your eyeballs will be quite dark because they're cooler, and your face and your nose is quite cold, like a dog as well. And so it's just a matter of the contrast. So if you were to use the right wavelength for the very cold object, you'd see it. But if it's not much difference from the background, it won't stand out.
So it's still sort of experimental in the sense that you have to wait and see what the temperature differences would be.
Yes. Yes, exactly. And if you're lucky in space, then there won't be any background. So you'll stand out.
Yeah, that's the hope. The other thing that...
Right, can we have another question now, please?
Okay.
So, from the chat channel, I've got Richard Bottle is asking, this may seem a trifle premature, but what sort of telescope or instrument do you think will replace JWST at the end of its life? Repeat that for me.
Yes, the question is it's a sort of messianic question. What comes next after the James Webb Telescope? Well, frankly, I think there will never be a thing similar to the Webb because it's too complicated. As we know, it started off at $500 million and ended up at $10 billion. You know, and $1 billion here, there. Sometimes it becomes real money eventually. And so I don't think they'll ever do anything super complicated. I think what they'll do more likely is rather specific designed missions to answer a specific question. So I think there could well be an interferometer in space, for example, or there could well be an X-ray mission. Actually, one of the members of the audience here would know more than I do about this, that will do something specific in X-rays that hasn't been done before. but I can't see them doing what I've sometimes called a Christmas tree, where you have lots of bits and pieces and things like the James Webb. So I don't think that'll happen again.
Now we're asked by somebody called Graham, what do you think is the most important objective of the JWST?
Yes, that is a very difficult one, because obviously it depends on your interest, although over the whole of science, one should be able to answer it. I mean, the big areas, I suppose, and people have talked about this a great deal, are looking at the very early universe, the first galaxies, to see if we can understand how galaxies evolve. So there is this question about what came first. Was it the stars or was it black holes? Well, of course, the Big Bang came first, but what was the first structures? And we don't really know what came first, chicken and the egg sort of argument. And the James Webb may help answer that question, and then we can use our fancy models in supercomputers to see if it agrees with our theories. So that'll be nice. But the other huge thing, of course, is exoplanets. And we don't know what we're going to find, whether we'll find imbalances in the atmospheres of exoplanets. For example, water vapor and methane, if they're wacky out of balance, it might indicate there is some kind of life form, vegetation or whatever on the planet. So there's a possibility of finding evidence for life, but it'd be controversial because there are other ways of producing an imbalance. But I think that will certainly be one of the drivers for the Webb. The two things, exoplanets and the early universe.
I'll take one more question from the chat channel, and then we'll see if we have any more in the room. Charles Draper asks, how does the orbit around the L2 point work? What's the size of that orbit?
Actually, it's pretty damn big. Now, I think people in the audience know more than I do about this, but I believe it's of order, it's tens of millions of miles, I believe. It's the yeah, well, you can do, yes. But it's not stable.
I've got to ask you to repeat the question.
Oh, sorry. The questioner wanted to know about the orbit, because the L2 is not a stable orbit. So things like the geostationary orbit is a fairly stable orbit around the Earth where these communication satellites are, but L2 is not stable. It's a bit like there being a P on top of a sort of sombrero hat. You push it one way, it goes down, rather than in a bowl. A stable orbit is where the P is at the bottom of the bowl. You push it and it goes back. Whereas in the L2, you push it and it goes off somewhere. So you actually have to station keep. That's the point. But I believe the orbit that it goes around is quite large.
Yeah, I mean, this was one of the very positive things about the launch that was provided by the Europeans. The launch was very, very precise indeed. And the way of getting to L2 is you have to throw the spacecraft from Earth almost exactly the right speed to just reach the point. It's a bit like a basketball player throwing a basketball towards a hoop. You throw it in just the right direction and just the right speed to reach the hoop and flop in. If you throw it too hard, it'll go off into deep space, which they didn't want to happen. You can't fire rockets the other way from the James Webb Space Telescope to bring it back again. So they had to launch it with just below the necessary velocity to throw it up towards the L2 orbit. And just to say that the L2 orbit is one of a number of semi-stable orbits around a three-body system where you have the Sun and the Earth-Moon system and a point beyond the Earth-Moon system where the spacecraft feels the gravity from the Sun, but also feels the gravity from the Earth and the Moon. And that adds in, and it tracks the Earth in the orbit around the Sun. So they had to be very, very careful when they launched, not to throw it too hard. And they had to add a little bit of speed later just to get it to the right speed. But it was very tricky and very risky. And that was only one of very, very many very risky things. So, and just to finish the thing, you don't just go to one point at L2. You actually orbit around that stable point in a very large orbit, about 1 million kilometers in diameter. So it actually goes round in this very large orbit very slowly, and it's occasionally nudged back into the right position. But it's, as Martin said, it's not a fully stable orbit, it's metastable, so you have to keep it in the right place. And the advantage of having it in this big halo orbit is when you look back towards the Earth and the Sun, you don't get the Sun directly behind the Earth, because it makes many things difficult. Sorry.
Just one thing to add to that, what Bob said. Very important, actually, because they got this so right, they didn't have to use a lot of gas, which it has some gas for manoeuvring on board, in the mid-course correction to get the thing in the right place. And this is crucially important because the James Webb, it was hoped, was going to last for 10 years, which is long, but the Hubble's been up there for 30 years. But because they didn't have to use a lot of gas to get it in the right place, we think it could last for 20 years, which is hugely important. I mean, the amount of science you get doubles, or more than doubles, because you learn things on the way. And then after that 20 years, I have to say, it may become space junk, unless we find some way to gas it up, which Bob says is possible, but I've not heard that it's possible. But unlike the Hubble, where you sent people up to fix things, there is no way to send people to the James Webb. There's no way. You might send robots. Anyway, 20 years would be good. And if medical science improves, I might see some of that.
So, who decides who gets time on? Can you repeat it?
Yes, the question is who decides who gets to use it, who gets time on this? Well, it's the same actually as for practically all large telescopes. And that is you apply, there's a call for proposals, and there's a bunch of committees in which some people in the room here have served on, many people actually, and they grade them, and some fraction, depending on how oversubscribed, how many more people want to use it, get the time. And it depends. If it's a big facility, popular, the oversubscription might be 10 to 1, maybe even 20 to 1. So just on statistics, you've only got a 1 in 10, 1 in 20 chance. That's not the way it works, because if you're very good at proposals, you have more chance. But it's peer reviewed. So just a simple answer is peer reviewed, and then you get the time if you get up there in the grades. But it's open to everybody, which is the good thing. It's not that you have to be in a certain country. Well, there's a sort of guideline for the amount of time that should be awarded, but it's only a guideline.
So you need to start polishing your application then. Any more questions in the room? Yes.
Yeah, as the first images start to come through, what are you looking forward to seeing first?
Me personally, interesting question. I'm involved in a couple of projects, which I can't go into because there's no time, but the one perhaps that's closest to my own interests is active galaxies. What happens near the black hole? Several of the nearby galaxies, nearby active galaxies, for reasons which we don't completely understand, but a lot of them are very dusty. They're enshrouded in dust. And so we haven't been able to study them particularly well yet. So I'm looking forward to penetrating through that dust, maybe looking to regions where these jets, so I said that stuff comes in onto the black hole, that stuff comes out in terms of jets. And we don't really understand how those two mechanisms, how the accretion, as we call it, inwards, and the blowing out through jets and winds, how those things go together. And so what the James Webb might do will tell us perhaps how these things are linked, going in and coming out. And so the nearby galaxies, there's 4 or 5 of them that I'm involved with, will be very interesting from my point of view. That's my own view. I mean, other people have different things they want to find out.
Yes, I'd like to ask you about looking at the very galaxies from the very early universe.
Yeah.
I mean, how much further back can it look than we've been able to up to now?
Well, I mean, I suppose the Hubble Deep Field is the one that's hundreds of hours of staring with the Hubble at one tiny bit of sky. I think it's maybe 100th the size of the moon, a little tiny spot, in which we see hundreds and hundreds of galaxies. But for one thing, that tells you how many galaxies there are, which is a ridiculously huge number. But in terms of looking further back, we're hoping to get to the period, well, of course we don't know because we haven't looked yet, but the period when the first galaxies were formed. And the Hubble can't do that because it doesn't go to the right wavelengths, and it's also not sensitive enough because of the area. So the combination of infrared and area should push us back to the first galaxies in terms of, it doesn't sound like very early, does it? A few 100 million years. But compared with 13.7 billion years, a few hundred years is pretty short period of time after the Big Bang.
Yeah, great lecture, thanks. The process taking the image, very much going through the alignment and then collecting the data, how long would that take as an average? Or?
You mean to actually, well, not very long, actually. I mean, it's like you're...
Sorry, could you repeat that?
Oh, sorry. How long does it take to make an image of whatever you're looking at?
Yeah.
Of course, it has to be sent back to Earth, and there's some processing that's done on the telescope. But like your mobile phone, I mean, actually, you just set an exposure time, you take it, and it's pretty much that length of time.
Sorry, on the lecture, you mentioned there was an alignment method.
Oh, I see what you mean. Yeah, well, actually, I'm not too sure about that, but every now and again, you will have to realign the mirrors because they don't stay perfectly aligned all the time. But that's built in. We call it, in the trade, we call it overheads. You know, it's a bit like money. You have these overheads, things that you didn't want to do, but you've got to do. And that's what we call in the observations, we call these overheads. And there's a certain amount of time built in. What it means is that the shorter the observation, the less efficient it is. Because the more the overheads of doing what you said, getting things aligned, is a higher fraction of the time you spend on your favourite object. So longer observations are better. But I don't think we know exactly how long that's going to take. It's going to have to be, we've got an idea, but it's going to be a fairly substantial amount of time. And then the telescope has to move from one part of the sky to the other part. And this fine guidance sensor camera has to then acquire a star to know exactly where it is and to lock onto it. And that's part of the overheads. Yeah, so it will be substantial, but it won't be sort of as much time as we spend on the object. It should be less than that.
From the chat channel, we have how many Earth-like planets will the JWST be able to look at to study their atmospheres?
Right. Well, I think Bob's the person again for this, but if I can answer it in general terms. I mean, they have to...
Sorry, could you repeat?
Oh, yes. How many Earth-like planets will the James Webb look at the atmospheres? Well, just to say at the beginning, you don't just look at the planet as you would the Earth from space and look at the atmosphere. You have to look at the star, the parent star, shining through the atmosphere of the star. So it has to be very perfectly timed and aligned. And there are, what do you say, 30 or so? I mean,
Michael knows.
Oh, Michael knows. Do you want to, how many, stand up your hands, how many stars, how many planets?
Well, there's currently considered something like 20 or 30, let's just say,
Okay.
Earth-like planets in the sort of planet world. So how many will be looked at?
I'll repeat that. Yeah. Well, by pure chance, Michael apparently has agreed with me. Apparently my estimate of about 30 is about right. And it depends then how many they can do. But the thing is, of course, that the time of the James Webb, 10 years, it won't all be done in the first year or the second year or the third year. It'll be done over a period of time. There'll be a program. So the longer that the James Webb lasts, the more of these things we can look at. But there is a fundamental limitation in there are only so many that are within range that we can do. And so we can re-observe them, we can look more detail, but probably maybe a couple of dozen, let's say, something like that. Yeah.
My question is actually quite a mundane and practical one. When looking at the structure of the JWST, you were showing how it is deployed by layering up the mirrors underneath those other mirrors. So I was curious to know how the reflection will take place, because what will those layered mirrors be doing, and what will the mirrors in the hexagonal mirrors be doing?
Yeah, I think that there's sorry. I was asked about the mirror structure of the James Webb. So there aren't layered mirrors actually. The thing that you saw with the 5 things, that was the heat shields. Although they're shiny, they're not mirrors. Whereas the gold things, the 18 gold things, are unobstructed, those things. So there's no layering there. You just have to get them all lined up. I know it's a bit confusing because it's so shiny it looks like it might be a mirror, but they're just the shields.
there any more questions in the room? Okay. Well, in that case, we've come to an end for this evening, and I'd like to thank Martin Ward very much for coming all the way from Durham to give us this lecture. I'm sorry about some of the problems we've had. For those of you who are online, we're in a different room from normal. We're not in Elwyn. We're in a smaller room downstairs with a different arrangement of the equipment. But this is, to some extent, good news, because upstairs they are installing a lot of new audiovisual equipment, which is going to improve things in the BRLSI considerably. So at least we have that to look forward to. And apologies for the glitches this evening. And as for the lecture, well, seeing how we're going to get even more knowledge of our position in the universe, I only wish that some of the world leaders would consider their position in the universe as well, because if they could take on board some of this knowledge, I think things would be very different. But can we all unmute and put our hands together for Professor Martin Ward, please?
Thank you. On the way out, if you want to have a look at the bits of the James Webb, they're here at the front. If you want to just, in passing, have a look.